Hey there, everybody. My name is Mr. Schnitzius, and I am one of the A squared I geometry teachers for this summer geometry class, summer 2020. Really appreciate the hard work that you guys are all putting in this first week. So this video is going to be about activity 2, lesson 1. And as you can see here from the title of this activity, we're going to learn about inductive reasoning. So you should be able to find this either on your ebook if you're logged in on your ebook, or if you've accessed one of the Springboard Unit 1 PDFs from the class website. This first problem is starting on page 13. So in this video, we're going to cover just a couple of things. We're going to learn about how to make conjectures by applying inductive reasoning. So there's some key vocabulary that we're going to get there. What is a conjecture and what is inductive reasoning? And then we're also going to do a pretty interesting activity that'll help us recognize the limits of inductive reasoning. So there are some things that inductive reasoning is really good for, but there's some other things where we might need a different type of reasoning to really solidify the conclusions that we've made. So here's the first example. This is number 1. 5 students attended a party and ate a variety of foods. Something caused some of them to become ill. JT ate a hamburger, pasta salad, and coleslaw. She became ill. Guy ate coleslaw and pasta salad, but not a hamburger. He became ill. Dean ate only a hamburger and felt fine. Judy didn't eat anything and also felt fine. Cheryl ate a hamburger and pasta salad, but no coleslaw, and she became ill. Use inductive reasoning to make a conjecture about which food probably caused the illness. So in this first example, there's already your first 2 vocabulary terms that we said we were going to think about. And I wanted to just do this example without saying precisely what those are so we can get a feel for what they mean, maybe just by solving a problem like we normally would if we were solving this in a puzzle book or something like that. Okay, so if this didn't say use inductive reasoning, what would we do? Well, we would probably look for some kind of common thread or pattern that was true about everybody that became ill. So JT became ill, Guy became ill, Dean did not become ill, Judy did not become ill, but Cheryl did become ill. So maybe at this point we're thinking, that's interesting. I wonder what all 3 of these people have in common. So JT ate a hamburger. Maybe the hamburger made her sick. Well, Guy did not eat a hamburger. Okay, so it's probably not that. Okay, JT had pasta salad. Oh, okay, Guy also had pasta salad. Oh, okay, Cheryl also had pasta salad. And then we could even look for a common thread in the people that did not get sick. Dean did not have pasta salad and he was fine. Judy didn't have anything, so she didn't have pasta salad and she was fine. So it looks like based on the pattern that we see in all 3 of the people that got sick, they all ate pasta salad. It seems reasonable to make a guess that it's the pasta salad that caused the people that got ill to become ill. So that's an example of inductive reasoning. Inductive reasoning is based on the patterns that we see, what educated guess can we make about what is causing something else? Or based on the patterns that we see, what do we think happened in this situation? And do we think that will continue to happen in the future? So the conjecture that we've made is it seems reasonable to guess that pasta salad caused people to become ill. And that word, a reasonable guess, is a good kind of introductory explanation for what a conjecture is. So let's look at some more precise definitions of what these terms mean. So a textbook definition of what inductive reasoning is, it's the process of observing data, recognizing patterns, and making a generalization. So an example that I thought of, my wife and I were just talking about our dog, whose name is Yoshi. Every morning he wakes up, he jumps off the bed, and he rolls around on the floor. So the fact that he has done this every day that we've been in quarantine here, that's like some data that we've observed, and we recognized a pattern. Every morning he does this. So what do we think he's going to do tomorrow? Well, tomorrow he's probably going to wake up, jump off the bed, and roll around on the ground. All right. So that generalization of I've seen this pattern so far, this is what I think is going on. I can make a prediction that it's going to continue happening in the future. That educated guess is a conjecture. A conjecture is a generalization or educated guess made from inductive reasoning. So now we're going to look at a couple of pattern recognition problems. This says use inductive reasoning to make a conjecture about the next two terms in the sequence. And we're going to explain the pattern that we used. So I've got this first pattern, A4C8 E12 G16. And it kind of looks like this is really two patterns in one. We're alternating between letters for the odd terms in the sequence, and then there's numbers for the even terms in the sequence. So it looks like it's first letter, skip a letter, then it's the third letter, then it's the fifth letter, then it's the seventh letter. So it looks like this blank right here is probably going to be the ninth letter, right? So that's A, B, C, D, E, F, G, H, and we're going to fill in I right here. So that takes care of the letter part of that pattern. And then we've also got numbers in the even terms in the sequence. So that's 4, 8, 12, 16. So that's a pretty easy pattern to recognize. That's increasing by 4 each time. So that's going to be 20 right there. 20 is 4 more than 16. So it doesn't just say to use the pattern recognition. Pattern recognition is a good example of inductive reasoning. It also asks us to explain verbally the pattern that we used. So if we were looking to explain what this pattern is, it could be we've got consecutive letters that are alternating with multiples of 4. So we've got another pattern down here. When you're doing pattern recognition with numbers, sometimes you can think, okay, what's the common thread between the consecutive terms? Are we adding the same number each time? Are we subtracting by the same number each time? Are we multiplying or dividing by the same number each time? So from 3 to 9, we could say that we're either adding 6 or multiplying times 3. Well, if we were adding 6, 9 plus 6 would be 15. That's not 15. So maybe it's multiplying by 3. 3 times 3 is 9. 9 times 3 is 27. So it looks like it works for those first couple of terms, times 3, times 3. But it's also really, really important that we make sure that it works for every term in the sequence, okay? So 27 times 3, that's 81. 81 times 3, that's 243. So if we were going to complete this pattern, we would say, all right, it looks like we're probably going to multiply by 3 to get our sixth term in the sequence. So 243 times 3, that is 729. And then we're going to multiply by 3 again to get the final, the 7th term in the sequence. And 729 times 3 is 2,187. So if we wanted to explain verbally what this pattern is, it's just multiply a term by 3 to get the next term. All right, so here are 2 more examples. So we've got 3, 8, 15, 24, 35, and 38, and 48. Well, it doesn't look like multiplication is going to be a good one to use this time because 8 is not a multiple of 3. So maybe we should think about what we're adding. So from 3 to 8, we're adding 5. But this is interesting because we're not adding 5 to 8 to get 15. We're adding 7. And then how much are we adding to 15 to get 24? We're getting 9. So by now, maybe you recognize the pattern. This first difference is increasing by 2 every time we add another term. So 5, 7, 9. This pattern in the pattern, you might say, looks like it's increasing by 2, so it would make sense for this to go up by 11. And 24 plus 11 is 35. And then from 35, we could add 13. So if this pattern is continuing from 48, we're going to add 15. 48 plus 15 is 63. And then if we increase 15 by 2, that's going to give us 17. And 63 plus 17 is 80. So how could we explain in words what that pattern is? The difference between consecutive terms increases by 2 each time. And this last one, D, is kind of a famous pattern. To see what is really going on here, we're going to still do the first differences. So we're adding 0 to 1 to get 1. Then we're adding 1 to 1 to get 2. We're adding 1 to 2 to get 3. We're adding 2 to 3 to get 5. We're adding 3 to 5 to get 8. We're adding 5 to 8 to get 13. So you can kind of see to get the third term, we added the first term and the second term. To get the fourth term, we added the second term and the third term. To get from 8, we added the number before it to 8 to get 13. So if we're starting here at 13, we're going to add the number before it, which is 8. 8 plus 13 is 21. We're going to add to 21 the number that came before it, that's 13. So 21 plus 13 is 34. And a good way to write out what this pattern represents is each term is the sum of the 2 preceding terms. This is called the Fibonacci sequence. Fibonacci was an Italian mathematician, and the Fibonacci sequence is really interesting because there's all sorts of ways that the Fibonacci sequence shows up in nature. So that's all we're really going to talk about with that for now. But I just wanted to give you that as you can kind of research that on your own a little bit more. So this is just a good way to introduce ourselves to inductive reasoning. When you see a pattern and you're making a generalization based on that pattern, that is a good example of inductive reasoning. Now, this next example is always really, really fun to do in class because this demonstrates some of the limitations on inductive reasoning. So we've got 4 different circles, and from each of the given points, we're supposed to draw all possible chords. You should remember from activity 1 that a chord is a segment, a line segment, so it has 2 endpoints, and the 2 endpoints lie on the edge of the circle. So these chords will form a number of non-overlapping regions in the interior of the circle. For each circle, count the number of these regions and then enter this number in the appropriate place in the table below. Well, it's pretty easy to see for this first one. We've got 1, 2 non-overlapping regions. So for 2 points on the circle, we get 2 non-overlapping regions. Now, we're going to fill in this entire chart and look for a pattern in this table. I went ahead and did these ahead of time because I didn't want you to have to watch me fill in every single one of those circles. Okay, so there's the first one. There's our 1, 2 non-overlapping regions. Then when we have 3 points on the circle, it's pretty easy to count this up. We've got 1, 2, 3, 4 non-overlapping regions. So we talked about additive patterns and we talked about multiplicative patterns in our first inductive reasoning examples. This one could go either way, right? Because I could say, what did I do to this 2 to get 4? Well, I could say that I either added 2 or I could say that I multiplied 2 by 2 to get 4. So we really need more information to help us get that. And so whenever we have 4 points on the circle, all the possible chords come out looking like this. So this one kind of divides out nicely. We've got 1, 2, 3, 4 regions on the top, and then 5, 6, 7, 8 on the bottom. So that's a really strong clue, maybe, that this pattern might be a multiplication pattern. 2 times 2 is 4. 4 times 2 is 8. And so it would seem reasonable to predict that this one is going to be 16. 16 non-overlapping regions whenever we have 5 points on the circle. So if we count this up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, so that actually is 16 regions. So if we're going to use this pattern that we've seen so far, whenever you add another point on the outside edge of the circle, you double the number of non-overlapping regions formed, right? That's what it looks like is going on so far. So we would predict that if we have 6 points around the outside of the circle, that seems like a slam dunk, right? 2, 4, 8, 16. If we double that, we should basically have complete confidence that this is going to be 32 points. 32 non-overlapping regions formed whenever we have 6 points. But the problem with that is we haven't proven that that is actually the case. We have an educated guess, and we've seen that educated guess, that conjecture, works for these first 4 pairs of numbers in the table. But what we don't know for sure is that it's going to continue. So when you actually draw out all the chords that you can, and you number all of the non-overlapping regions formed, it turns out that there's only 31. There are only 31 non-overlapping regions formed by 6 points on the outside edge of the circle. So why did we take the time to go through and look at this example? Well, just because a pattern holds true in the beginning, or even if it holds true for several cases or even many cases, that does not guarantee that it will continue to be something that's true forever. So in order to know for sure with complete certainty that a conjecture is true, we will need to complete a proof, and we'll discuss that in the next video in activity 2-2. So that's just a demonstration of the limits of inductive reasoning. Inductive reasoning is great for recognizing patterns and making conjectures, making educated guesses about what's going on and the information that you see. But just because that conjecture is true for a while, that doesn't mean that you know for certain that it will always be true. So here are 2 more examples for us to think about. This is number 9 in the book PDF. This is on page 17. The table below represents the function f of x equals 2x plus 5. Based on this table, Trent conjectures that the value of f of x is always positive. Is Trent's conjecture true? Explain how you know. So this is kind of nice because this is an algebra question in a lot of ways. You know, if you were taking a test in Algebra 1 class and your teacher was asking you to match a table to an equation, hopefully they said something like, be sure that you check it for every single ordered pair. Okay, don't just say that it works for the first couple and then circle that equation. You got to make sure that it works every single time. So we're doing the same type of thing, except what we're investigating isn't whether or not this equation is correct. We're investigating whether or not the values of f of x are always positive. So if you're just flying through a question like this, you might look at this and say, well, 1, that's positive. 3, that's positive. 5, 7, 9, they're all positive. You might think, yeah, that's true. But if the conjecture is true, it needs to always be true. So another way that I could ask this question, is Trent's conjecture true? I could ask that as, is it always true that the values of f of x are going to be positive? Okay, and it should be pretty easy to sniff out that if we choose some negative values of x, like if x is negative 3, 2 times negative 3 is negative 6, negative 6 plus 5 is negative 1. So that's what we call a counterexample. This example right here shows us, no, we have one situation where f of x is not positive, therefore Trent's conjecture is false. So to write that answer out, we could say no, f of negative 3 equals 2 times negative 3 plus 5. Well, that's equal to negative 1, which is not positive. So this is an example of a counterexample. Oh, sorry. F of negative 3 is a counterexample. That is one situation, one situation where you show that your conjecture is actually not true. If you can show that it's not true for one case, then you've shown that it's not always true, and that proves that the conjecture is false. Okay, here's one last example. Monique tosses a coin 3 times. She gets heads each time. Based on this pattern, she makes the conjecture that she will always get heads when she tosses the coin. Do you think that Monique's conjecture is reasonable? So this is a lot like the last one. If you're just whizzing through this question and thinking, well, that seems like it should make sense. I mean, it's been heads every time so far. But the thing that's tricky about this is her conjecture is that she will always get heads. So in order for this conjecture to be true, this always word is making it really hard for that to be a true conjecture. Maybe she gets heads the first 3 times. Maybe she even gets heads the first 10 times. But if you know about probability, you know you've got a 1/2 probability of getting heads, but also of getting tails each time. So as long as tails is a possibility, it doesn't seem like Monique's conjecture is reasonable. So let's read about why that is. She's basing her conjecture only on 3 tosses. She could have gotten heads just by chance, even if the coin is fair. And so just based on inductive reasoning, there's not enough evidence to conclude that she will always get heads. So just to wrap up what we've seen so far, kind of to summarize what we've learned about inductive reasoning. Inductive reasoning uses patterns, data, observations, and examples to make a conjecture. That conjecture is an educated guess. You cannot know with certainty that your educated guess is true for all cases without examining every single case. And that's a real problem because If you think about every single case, if you think about Monique's example, how many possible times could you flip a coin? Well, you could flip a coin forever, theoretically. So if you flip a coin, a fair coin, 1,000,000 times and you get heads every single time, that's still not a proof that you're going to get heads every single time. So this fact that you have to examine every case to know for sure that your conjecture is true in inductive reasoning, it makes proving something with inductive reasoning really, really difficult. So in the next video, we're going to learn about a different type of reasoning to prove that conjectures are true. So we'll learn about deductive reasoning in lesson 2-2. Thank you guys so much.